to you, okay?
Okay.
And thanks for accepting our invitation. Well, let's just wait for one minute.
Yes, no problem.
Okay, let's start. Hello, everyone, and welcome to another talk in our webinar series. I'd like to remember that this webinar is also being streamed live on YouTube. You can find the link on our website, or you can access it on our YouTube channel, /LIneA MCTI. Today, we have Santiago Ismael Ferrero from the University of Oslo presenting a talk about a unified scenario for the origin of spiral and elliptic galaxy structural scaling laws. Santiago, thank you very much for accepting our invitation and being with us. The floor is yours.
Okay, thank you for the introduction. Thanks, Rodrigo, for this invitation. It's a pleasure for me to give a talk. So I am currently now doing a postdoc at the University of Oslo, working mostly on Euclid mission in the Cosmological simulation working group. But I have a background in my PhD working on galaxy formation and galaxy evolution. So I still trying to do often some work on this field. And for today, I would like to talk about this what's a paper that we submit a couple of weeks ago, and in where we try to understand in a single way the galaxy structural scaling law for both elliptic and spiral galaxy. So for those that know the logo, you can see that I dared to change the LIneA logo because when I received this invitation from Brazil, the first thing that came to my mind when I think in Brazil is, of course, caipirinha. So there you have like a new logo of LIneA, so you can use it, feel free. Okay, so this work was done with some collaborator from Canada, is Julio Navarro, and from Cordoba, Mario, Jose, and Damian. So Mario was my PhD supervisor in Cordoba when I did my PhD. So let me get some introduction about this topic. So as I'm sure that you know that 100 years ago, Hubble realized the real nature of galaxies. And he introduced the classification of galaxy based on their morphology, spiral and elliptical galaxies. Okay, and from that time until now, several people have extended this separation, this classification of galaxy, not only by morphology, but doing this, doing the creating like a gap in all the properties and scaling law that both kind of galaxy follow by separately. Okay. So I'm not going to read the list, but you can see that for each property or for each law that one kind of galaxy follow, there is always an antagonist in the other. Okay, so discoidal, spheroidal, blue, red, gas rich, poor rich. So the list go and go. Okay, so the idea we want to transmit is that exists a gap between these two kind of galaxy. And it started with the morphology by Hubble and has extended to all properties and scaling law. So what we try to do is like bridge a gap between these two populations by studying or merging the scaling law related to velocities, size, and mass of this galaxy, which are like the main scaling relation or the most known scaling relation for early type and late type galaxy. So we have the Tully-Fisher and the Faber-Jackson relation, for example. So the key question, well, before that, the scaling law that we are considering for this analysis are those that live in this space of mass, radius, and velocity, okay? And the key question that we want to address is why a spiral and elliptical obey different scaling law, okay? So it's really known that in this space of radius, mass, and velocity, of course, we can express the mass as luminosity, mass or luminosity, or we can also express this axis with a surface brightness because it's just dividing by the radius of the galaxy, by the size. Okay, so in this space, there is a lot of famous scaling relation and property that follow both samples. And these are so important that most of them have their own name, like the Freeman law, Kormendy, Tully-Fisher, Faber-Jackson, the N sigma relation. And of course, we have the fundamental plane, which is not a projection, but is a plane which is in this 3D space. Okay, so we analyze all of them. We analyze the property of these two different kind of galaxy, trying to unify the way we understand the relation for these galaxies. Okay, so let me introduce briefly some of them. I'm sure that most of you study or know it from before, but just to summarize, the Tully-Fisher was introduced in 1975 by Tully and Fisher, and it's a simple correlation that follows a spiral galaxy between the luminosity and the rotation velocity. Okay, so as bigger the luminosity of the galaxy, higher the rotation velocity of the galaxy. And it seems that the galaxy follow a power law where the luminosity goes like the velocity cube, okay? And one year before that, Faber and Jackson introduced a same relation, but for elliptical galaxy, for early type galaxy. In this case, velocity, the velocity is a velocity dispersion, okay? Because elliptical galaxy are systems that are supported by dispersion, while spiral galaxy are supported by rotation. So in one case, people measure rotation velocity, and in the other case, people measure velocity dispersion. Okay. And in this case, for the Faber-Jackson relation, the luminosity goes like sigma, like the velocity dispersion, to the 4. Okay, so it's a bit different, the slope of this relation. Of course, later work confirmed this relation, introduced it in the 17th, and were very useful to improve the fit with lower uncertainty, because a lot of new observation, galaxy observation, were measurement, well measured, and this reduce the uncertainties, getting a better fit on both scaling law. Okay, so these two relations are really has been established very, very well during the time. So many questions arose about this relation during the years, and one of the most important is about the scatter of the Tully-Fisher. Okay, where does the scatter came from? Okay, so if you take a velocity, rotation, then the scatter of the luminosity is really teeny, it's tiny. Okay, and these relations are important because people use this relation as a distance indicator. Okay, because you have rotation velocity, and by measuring the rotation velocity of a galaxy and using this relation, you can get the luminosity of the galaxy, the absolute luminosity, and then with the magnitude, the apparent magnitude, you can get the distance of the galaxy. Okay, and why the Tully-Fisher has this slow scatter is something that people is still asking themselves. So then people try to see if there was also a correlation with the radius. Okay, and for Tully-Fisher spiral galaxy, there is not correlation of this property with the radius. Okay, for a given velocity, it doesn't matter the luminosity that the galaxy have. It doesn't depend of the radius. But it's not the case for elliptical galaxy. There is a dependency for elliptical galaxy with the size, with the radius. Okay, how is this dependency? For a given velocity, bigger galaxies are more luminous than a smaller galaxy. Okay, so both smaller and bigger galaxy follow a Faber-Jackson relation, but with different 0 points. Okay, with different amplitude, let's say. So this introduced like a bigger scatter in the Faber-Jackson because this dependency of the radius, and then this made understand that luminosity goes instead of go like sigma times 4, luminosity goes with sigma squared times r. Okay, because of this dependency with the radius. And this is the way that this is the origin of the fundamental play, where one of the projection is the Faber-Jackson, this relation between the velocity dispersion and the luminosity that I said before. And for elliptical galaxy, we have this fundamental plane, which is like a plane in the space, mass, size, and radius, and velocity, sorry. So the fundamental plane is there because there is a dependency with the radius, okay? But why this doesn't happen for spiral galaxy? Why spiral doesn't show this dependency with the radius, while elliptical does? So that is one of the question we want to answer. Of course, you can see here that there are many studies where this slope in the power law change a bit from one to another author. Okay, so you can find like the luminosity goes with B time cube or time cube 3.3, or also for the the Faber-Jackson, the values of the slope change also a bit. Okay, so it's not so strict. It's not like a single value for this correlation. But in general, the galaxy follow this fit, this plane for the elliptical and this power law for spiral galaxy. So again, people ask themselves, why is different from spiral than for elliptical? What is the origin of this correlation? So just to give a basic theoretical description on how do you obtain this relation in the system. For elliptical galaxy, the Faber-Jackson, the relation between the mass, well, the fundamental plane, is understood as a reflection of the virial theorem, okay? So you have a virial theorem if you assume that the double kinetic energy is equal to the potential energy, then it is simple to deduce that okay, sigma square go with the gm over r, and then by cleaning the m, you get the fundamental plane. Okay, so its mass is equal the velocity dispersion square times r. Okay, so and that is the fundamental plane, this fit that I showed before. But for a spiral, we can start also from the virial theorem, but if we do the same, of course, we will get the same relation that Faber-Jackson of the fundamental plane, and it's not what we want for a spiral galaxy. Okay, so in this case, we need to take different ways, and for a spiral galaxy, we assume the virial term, and also the fact that following a spiral, a spherical collapse model, the density of the halo must be a constant. Okay, so this is a constant. So you assume a density constant that goes like the critical density 200 times the critical density, blah blah, and then you got the expression for this density, and you can replace this in the virial equation, and then you get the Tully-Fisher, that the mass go with the velocity cube. Okay, and that's the Tully-Fisher. But of course, why we need to take different ways for one than the other is not clear, and never was clear, let's say. So in this work, we try to answer it by using cosmological simulation to unify a description for this law of both early type and late type galaxy, spiral and elliptical galaxy. So we use Eagle and Illustrate hydrodynamical simulation. I'm sure that all of you know this simulation. Both are state of the art in hydrodynamical simulation. So we use for both simulation, we use the box of higher resolution that has, well, higher resolution and cosmological volume, because we have enough galaxy. We want to make a statistic of the galaxy. So we use the box of 100 megaparsecs for both simulation. And this simulation include a wide range of physics process, okay? Feedback, AGN, star formation, relative cooling. So are very, very complete simulation. And just to show you one example of how success are these simulations, this is the luminosity function for Eagle. And they reproduce the stellar mass function at redshift 0. Well, they are calibrated to do it. They're calibrated to match property at redshift 0 of observed galaxy. But there is a good match in both extreme of mass for dwarf galaxy and giant galaxy as well. So to give you just an idea, for example, for a galaxy of the mass of the Milky Way, for example, which is this vertical shaded area here, in Eagle you can find 500 simulated galaxy of the order of the Milky Way. Okay, so in our case, we are going to use galaxy from this simulation with a stellar mass greater than 10 to the 10. So our sample include 100,000 of galaxies. So it's a statistical performance is enough, let's say. Also, both simulation reproduce the morphological classification introduced by Hubble. So they are good at reproducing the number of galaxy and the morphology of the galaxy. So here you can see an example of elliptical galaxy and a spiral galaxy in Eagle. Okay. So the next we did is to separate the sample. We took all the galaxy from the simulation. We analyzed the way to separate into a spiral, late type, or elliptical, early type galaxy. So we use two different parameters to do it. One, which is in the y-axis, is the gas fraction, which is the gas mass of the galaxy divided by the stellar component. And the other one in the x-axis is the key rod. It's the kappa rod, which is like it's a kinematical parameter. We tell you if this value is close to 1, then it's a system that is supported by rotation, and it is close to 0, it's a system that is supported by dispersion. Okay, so we select a late type galaxy, a spiral galaxy. Those like have this kappa rod greater than 0.6, and also those galaxies that have more than 10% of gas. Okay, so the blue are our late type galaxy for Eagle on the left and TNG on the right. And then the opposite condition for early type galaxy with less than 10% of gas and with this kappa rod parameter smaller than 0.6. Then in gray, you can see those galaxies that are intermediate type, okay? So let's start with the analysis of the simulation. We find something similar to observer Tully-Fisher. There is like a bit more scatter in the TNG simulation, which is in the bottom panel. So we have a stellar mass and the circular velocity. But I am not going to discuss how well they reproduce observer results, because that is not the point I want to address, okay? We want to understand the difference between a spiral and elliptical galaxy, okay? So this is the case of a spiral galaxy. They follow a Tully-Fisher relation, like an observed Tully-Fisher relation. And these are the early type galaxy. Elliptical galaxy, in this case we have stellar mass and velocity dispersion. Okay, and they also follow like a Faber-Jackson relation, like the observed Faber-Jackson relation. So we thought in the way to think or analyze this thing together, and the way we tried to identify was thinking or use is to, for elliptical galaxy, we measure velocity dispersion in the line of the sea. Okay, so it's one component of the velocity, and we assume that the other two are similar. Okay, so that is the case for elliptical galaxy. While for a spiral galaxy, what we measure is the velocity rotation, while the other two components are almost zero. Okay, because the system is supported by rotation. So stars are rotating. Okay, so if you multiply the velocity dispersion by square root of 3, you get this. Okay, so This is not like the Wolf relation, which is a relation between the circular velocity of a galaxy and the velocity dispersion. And this is a factor of, right, square root of 3. Okay, so there are not practically difference between one or the other sample. So this is a way like express both velocity dispersion and circular velocity in a 3D way, okay? So then if we want to see the radius, how are the radius of this galaxy? And in this case, it's not the same, okay? Elliptical galaxy has a systematically smaller radius, the red one in this plot. So for size, the morphological types matter, okay? Comparing this simulation, again, that is not what we want to do, but comparing with observation, a spiral galaxy on Eagle match observed spiral galaxy. And TNG, elliptical galaxy, match observed elliptical galaxy, okay? So neither of both galaxy are success in reproduce both the size of both samples at the same time, okay? Eagle is doing well with the spiral galaxy and TNG is doing well with the elliptical galaxy, okay? So you can see from this plot that for a given stellar mass, for example, at 10 to the 10.5, you can find galaxy with which an order of magnitude difference in radius. Okay, you can have a galaxy of 1 kiloparsec. This is, sorry, this radius is effective radius. Or you can have a galaxy around 10, 12 kiloparsec. Okay, so they are really, really different in size. So why they have the different size? So the first thing that we ask ourselves is, do they live in different halos, in halos of a different size or mass? And that is not the case, okay? So this is Eagle. So here you have like the stellar mass function, the stellar component, the stellar mass of the galaxy as a function of the halo mass. It's like the abundance matching relation. You can see there the dashed the black line is the Beruzzi, and solid black line is Moster. And okay, both simulation, let's say, that follow the abundance matching of this Beruzzi and Moster, not so well for the extreme of massive galaxy. But it seems that both type of galaxy, early type or late type, live, let's say, in the same halo. There is a small difference that elliptical galaxy seems to live in halos a bit more massive, but the difference is too low, and this difference doesn't explain the difference in the size that the galaxy have. Okay, so we're trying to choose, let's choose a galaxy and make an example. For example, this the green point, it's a galaxy of 10 to the 10.5 stellar mass. And this galaxy lives in a halo of 10 to the 12, okay? So let's do a theoretical simple model to explain the velocity we measure in this galaxy, okay? So imagine you have a halo of 10 to the 12 solar masses, and you put in this halo a galaxy, you put in this halo a galaxy of 10 to the 10.5 solar masses, okay? As I showed before, there is a huge difference in size that you can find in galaxy, from 1 kiloparsec to 12 kiloparsec. So it's one order of magnitude, okay? So, so we put a compact galaxy of 1 kiloparsec in this halo. And we also put a galaxy of 12 kiloparsecs, effective radius, okay? So what happens if we put in the same halo, the same galaxy mass, but with different size? So what are the velocity that we measure for both cases? Okay, so this curve shows the velocity. Okay, so blue is the galaxy component, the star, red is the dark matter halo, and black are the different total velocity that you measure, circular velocity that you measure in that radius. Okay, so for example, for a compact galaxy of 1 kiloparsec, this is what we get. Okay, so blue is the stellar contribution to the velocity, red is the dark matter, and the green point here denote the velocity that you measure, the circular velocity that you measure in the effective radius, which in this case the effective radius is 1 kiloparsec. Okay, so what you measure is this velocity. So in this case, the velocity is dominated by baryons. Okay, it's totally dominated by baryons. The dark matter doesn't contribute at all at this scale. So in the opposite case, when we put a galaxy with extended galaxy of 12 kiloparsec, so it's different. Then again, the blue is the component of the galaxy, red is the dark matter, and black is the total velocity. And the gray point is the velocity that you measure in the effective radius, which is 12 kiloparsec. Okay, and in this case, the velocity that you measure is dominated by dark matter, by the halo. Okay, so the galaxy doesn't apport too much to the velocity when the galaxy is too extended at this scale. So it's very different. Okay. So in intermediate size, a normal size, say a galaxy of 4 kiloparsec size, we get a rotation curve almost flat. The black is almost flat. And in this case, both components contribute to the velocity of the galaxy. Okay. So if we consider all the case, okay, if we consider a galaxy with many size, again, the same mass of the galaxy, the same halo, you can see that this grain point, all these grain points are the velocity you measure in the effective radius if for different sides of the galaxy. Okay, so the size of the galaxy is given by the radius where you measure the velocity, the circular velocity. Okay, so you can see that there is a light green point here. If you are going to measure after this size, you will get always like the same velocity, the same circular velocity close to 150. Okay, but if you are measure your velocity, if your galaxy has a size smaller than this light green point, which is 4 kiloparsec, then the velocity you're going to measure change a lot with the radius. Okay, so there is a dependency with the radius here. Okay, and as I said before, elliptical galaxies are more compact than a spiral galaxy. Okay, so there is like this critical radius that seems to separate samples, and elliptical galaxy have effective radius that are smaller than this critical radius, and a spiral galaxy have effective radius that are bigger, are more extended galaxy. Okay, so for a spiral galaxy, we are always measuring like the same velocity. Okay, and that is the explanation why the Tully-Fisher doesn't have a big scatter. Okay, and that's the explanation why the Tully-Fisher or the spiral galaxy doesn't show a dependency with the radius. It doesn't matter the radius. The galaxy is big enough, and you are going to measure always the same velocity for a galaxy of the same mass but different size. Okay, but on the other hand, elliptical galaxies are compact. are more compact, and you are always, the size are always, well, always, most of the case, are smaller than this critical radius. So then the velocity change a lot from one galaxy to the other, where the radius are both small but different, okay? And this introduced the dependency of the radius for elliptical galaxies, okay? So then we repeated this example, but for 4 different beams. So 4 different halo with 4 different galaxy. You can see them in the different color here in the plot, and we repeat the same, okay? So here we have, again, this is the circular velocity and the effective radius, and these color lines are the same that I show here, the green, okay? But the difference is here I am plotting in line scales, and here I am plotting in log. So that is why it looks different, but it's the same, okay? 4 different redshifts. Curves are the model, and the dashed line are the contribution of the star, and dotted line are the contribution of the halo, okay? And you can see that points, I didn't say, but the points are galaxies that live in this shaded grid area, okay? So we select the galaxy that are in that stellar mass for each beam. So you can see that the model, this simple model that we create, and this simple model is assuming a relation for a given stellar mass. You assume a halo mass taken from abundance matching. Then you assume a Navarro-French profile for the halo. You assume a concentration for the halo, and you assume you model the contraction, because after the galaxy form in the center of the halo suffer a contraction, okay? And you have to model it, the contraction. So this is a simple model, and galaxy seem to follow these color curves, okay? Again, I mean, the simulation do not need to follow our rudimentary model, but it works, okay? If you see, for example, green point, the green point here, spirals are located on the right because are bigger, and elliptical galaxy are on the left, okay? So the same for TNG. Is the same for TNG, okay? And just to put some number here about this impression I presented before, if you consider, for example, these are 4 curves, okay? 4 different, this is the gap between these 4 lines are the stellar mass. So we are considering a galaxy of 10.1, and a galaxy of 11.3, okay? So the difference in mass is 1.2, okay? And if we analyze the stellar component, the contribution of the star to the velocity, you can see that from here to here, this dashed line to this dashed is 0.6, the delta in velocity you have, okay? So then if you do this basic equation, you get that the mass is proportional to velocity cube, okay? And on the other side, if we see the radius, for a change of mass from 1.2, we have a difference of 1.2 in radius, okay? So that gives you that the mass is proportional to the radius, and if you combine, then you get the fundamental plane, okay? So we analyze the stellar component because elliptical galaxies are compact and are in the size or the place where you are going to measure the velocity. There are not contribution of the dark matter there. It's just baryon, okay? So that is why we are only considering the contribution of the dashed line, the stellar component, okay? And for elliptical galaxy, they are in the outer part, the spiral galaxy, sorry, outer part. So the only thing that important is the contribution of the halo. So again, for a delta in mass of 1.2, the difference between this dotted line is 0.4, and this gives you that the mass goes with velocity cube. And of course, these lines are completely flat. Okay, so the delta in radius is infinitive. So you get that the mass goes with r times 0, and the combination, you get the Tully-Fisher. So the fundamental plane and the Tully-Fisher are just a reflection of the domain of baryon in the inner part for elliptical galaxy, which are smaller, and the domain of dark matter halo in the outer part, because spiral are more extended. Okay. And the bonus we do with it is to create like a secondary distance indicators. As I'll tell you, Tully-Fisher and Faber-Jackson works as a distance indicator. Okay. So what we did is change. It is the same plot, the same curve as before, but instead of put the size here, the radius, we put the surface brightness, because both things now are independent of the distance. Okay, so we put again this grid. This grid are all the same line that I showed before, but with different stellar mass. Okay, and the point under are the simulation are the galaxy in the simulation. Okay, so you can put the galaxy there in this grid model and interpolate between the two lines that are closer to each point and get a prediction of the mass. Okay, the line, you take the mass of the line that is closer to your point. And this is what we get. We have in the stellar mass of the galaxy and the prediction mass that we get with this simple model. And you can see that there is a good match, okay? And what is surprising is that the scatter here is smaller than in the Tully-Fisher. And which is more important is that it doesn't depend, this distance indicator doesn't depend of the morphology. You don't need to know if your galaxy is early type or late type in order to use Faber-Jackson or Tully-Fisher. You just put your galaxy here and you can get an estimation of the distance of the galaxy. Okay, then of course I will go faster in this part. We did the same for the observed galaxy. We take the sample of Pisagno and Spark for spiral galaxy, and Atlas 3D and Slugs for elliptical galaxy. And of course it's the same, doing this change the velocity. There is a small difference in the velocity, but it's nothing compared with the size. You can see again that the size between early type and late type are very, very different, covering more than one order of magnitude. Okay, we repeat this model with different beams. Now we use 3 beams, and you can see the scatter is a bit higher because we are, of course, using observed galaxy where the uncertainties are bigger. And I didn't say, but this black line here denotes the critical radius. This critical radius where you have a dark matter dominated or a baryon dominated. So you can see this radius corresponds to the point where the contribution of the dark matter and the baryons is the same. Okay, and you can see that galaxy, for example, you see the green, spiral galaxy are located to the right of this critical radius and elliptical galaxy on the left. Okay, so all is the same, the math, and you get something that is closer to the fundamental plane and the Tully-Fisher with a small difference in the slope, but it's something expected. Okay, and for the distance indicator, it's the same. We create this model, and we put there all the observed galaxy with a great point here, and after interpolate, you can predict the mass of this observed galaxy. And the scatter here, it's around 0.17, while the scatter in the Tully-Fisher for this observed galaxy is 0.27. Okay, and this scatter is what import in when you are going to use this scaling law for distance indicator. Okay, so this distance indicator is as competitive as Tully-Fisher or Faber-Jackson, and it doesn't matter the morphology type of the galaxy. Then there is, well, there is a pink and blue line because, as I say, our model is a simple model, assuming a concentration and a contraction of the halo. And for example, we used netting contraction of the halo, but if we, which correspond to the pink line here, the pink shaded area. But if you change, if you use another contraction model like the adiabatic, then you get the blue, which is a perfect match of the stellar mass of this galaxy. Okay, so this is a rudimentary model that can be improved a lot by tuning the component of the model. Okay, so there are two things that like the take-home message I would like to give you. And the first is that Tully-Fisher and fundamental plane scaling relation emerge as a consequence of different dark matter component inside the effective radius. Okay, what I showed is that the difference in between fundamental plane and Tully-Fisher or elliptical and spirals is because we are measuring in different radius. Okay, for elliptical we are measure velocity in radius where the dark matter doesn't apport to the velocity. Okay, elliptical are smaller enough, so there is no component of the dark matter there. While spiral galaxy are extended galaxy, bigger, are the radius are bigger than this critical radius, and then we are considering well, there is a contribution of the dark matter which is more important than the baryon. Okay, and this is why in the theoretical equation I showed in the first part of the talk, I introduced this constant density of the halo for a spiral galaxy in order to go from the virial theorem to the Tully-Fisher relation. That is the extra component that the spiral galaxy have, because they take into account the dark matter. Okay, and the second message is that this unified distance indicator that you can use for galaxy, and it doesn't matter the type of galaxy you are considering. You don't need to do if they are elliptical or spiral galaxy. You can estimate the distance of the galaxy by using this simple model that, of course, can be improved. So that's all. Thanks.
Thank you, Santiago, for the very interesting talk. We now have time for some questions from the audience. So questions?
Hi, this is Julia. Can you hear me?
Hi, Julia. It's a little low. Would you turn a little bit your volume up, if possible?
Is it better?
Yes, yes.
Hi, thanks for the talk. Very, very interesting. I'd like to ask you about those other groups that are out of the classification for early and late times.
Yes.
Those gray points in the when you show the separation.
Yes.
How they behave and how could they be included in the model?
Well, as I say, for the model, it doesn't matter the galaxy you're considering, because we separate the samples, but then we use all of them in the analysis. And something that we found in a previous work of the Tully-Fisher for Eagle, for example, if it doesn't matter the kind of galaxy you're considering, all of them follow the Tully-Fisher relation, they say. And this introduced like a bit as a scatter, but in the analysis, we are considering, for example, yeah, this is TNG. So you can see Gray points are also in behind of the plot. And also here, the galaxies that are
like intermediate types.
Yes, yes. You can see in the prediction of the mass on the right plot, the gray points that are behind are the intermediate type. And there is no difference with the others. Okay. So in this analysis, if you want to use this, you can use any kind, not only elliptical or late type. Okay. And of course you can improve, because the way we separate the sample in the simulation is not so complex way. We did a simple one. Okay. So you can go deeper and it will be the same. So that is the reason, because we didn't
emphasize that.
Yeah, emphasize in the way we separate the sample of how precise we are. So yeah.
I see. Thank you.
Welcome.
Okay, more questions?
I have a question. So first of all, thank you very much, Isma. Was really, really nice, very interesting. My question is regarding how you measure the velocity, this circular velocity on the simulation. Is really that you are measuring the velocity, or you are inferring the velocity from the
what we do is GM over R, and that is that is what people used to do on simulation when they compare the circular velocity to the let's say to the rotation velocity of observed galaxy. So you use GM over R in the effective radius.
For all the galaxies, for
the spiral galaxy, yes, and for elliptical, well, for the elliptical as well. But as I showed before, if you take the velocity dispersion and the circular velocity, and you apply this factor of square root of 3, you get almost the same. There is no big difference there. And we also analyze that what you say is what happens if you take GM over R, and what happens if you really take like a projection of the galaxy and measure the velocity rotation. And again, there is no big difference. There is some scatter there. When you use GM over R, the scatter is lower, of course. But both way to calculate follow the same train. It's almost the same. Yeah.
Thank you. Perfect.
Okay, thanks. More questions? If you are on YouTube, you can put your question in the chat and we will redirect them to Ismael. In the meantime, I just want to extend the congratulations from some users on YouTube on your very good presentation from the user Matias Ferrero and Poli Baigo.
The surname is my brother. Why that's nice. Why he's so.
Okay, so more questions?
Hello, it's Ellison here. I have a question, and I was wondering if this limit radius could explain why the bulge seems to an elliptical galaxy.
Why what?
In terms of, if this limit radius that
the critical radius.
Yes. So if this could explain the behavior of the bulge of spiral galaxies, which seems with an elliptical galaxy.
The bulge, you say?
Yes.
What do you mean? If this can explain why elliptical galaxy?
Yes, because for example, in the bulge we have this behavior of stars that is more similar to elliptical galaxies, right? So there's a dispersion of stars there.
Yes.
So I was wondering if this theoretical model that you are suggesting, it's useful for explaining the bulge in the spiral galaxies.
Well, we didn't think in that. I think that yeah, it's a good thing to do. A next step to control to see if that can explain the bulge in spiral. Of course, this critical radius is not separating. It's not separating both samples exactly. You have like a scatter, and of course you have galaxy from one sample that goes to the other side. And I guess that will be good to what you say, for example, to analyze spiral galaxies that are on the size of elliptical galaxy, and if this is related with bulge or not. But yeah, we didn't do so far. Yeah.
Okay, thanks.
Welcome.
Thank you, Ellison. I think we have time for one last question. Okay, I think we are out of questions now. Well, let's thank Santiago again. Thank you very much for accepting this invitation and giving this amazing talk. And for if you in the future, any of you that are with us now, if you want to watch this amazing webinar, you can refer to our YouTube channel.
Yeah.
Yeah, please. And also for the next week's webinar, we will have Peter Hatfield from the University of Oxford talking about the relationship between galaxies and their dark matter halos over cosmic time. And thank you again, everyone, for attending, and a special thanks to Santiago. Okay, so
you're welcome.
Thanks, everyone. Have a great day and see you next week.
Bye.
Bye-bye.